a little bit here for you?
No.
So for new people, we are discussing chapter 2, which is a short review of quantum field theory in Minkowski spacetime. So to be sure that everybody is in the same wavelength. So I started with the classical theory last day. I finished that section. And essentially, what I was trying to do is the classical theory of a real free scalar field. It satisfies the Klein-Gordon equation. Mu square phi equals 0, where mu is just the mass divided by Planck constant. This is classical, but you need the Planck constant in order to have these mu dimensions of 1 over length. And what we did essentially was to find solutions to solve that equation. So in the language I was introducing, what I wanted to do is to find a basis of the space of complex solutions to this equation. This equation is linear. The space of solutions is going to be a vector space because linear combinations of solutions will be solutions. And even though the field is real, I look for complex solutions, and this guy will be just a real element of that space. And we found that using Fourier expansion is very useful. So we decompose the field in an infinite amount of harmonic oscillators, and therefore a basis of that space is made of elements which oscillate with positive frequency, omega of k t minus kx. I was using this convention for the normalization, you will see why. And also the same guy's complex conjugated. Minus kx over 2 omega for all x, of course. One of this couple for all values of the wave vector k. And you can check that this guy is solution of this equation, this guy is also solution of this equation, and they form a complete basis. So this space has infinite dimension. For each k we have 2 complex dimensions. So it has really infinite times 2 complex dimensions. And this is what we call, these modes is what we call positive frequency modes, and these guys are negative frequency modes. So what we have done is to decompose this guy in the sum of 2 subspaces, one of positive frequency modes and the other of negative frequency modes. And of course, this subspace is just the complex conjugated of this guy, because this basis is the complex conjugated of this one. And therefore, with that in our hands, we can write the most generic solution to the Klein-Gordon equation, which will be a linear combination of my bases. The sum is a continuous sum, because k is continuous. And we have a coefficient, one element of the basis. Sorry, omega of k is just the positive root square of k squared plus mu squared. So I will not write the k dependence anymore. Yes, omega. This x over 2 omega plus a conjugated. So phi is a real field, so it's going to be this plus the complex conjugated. So the constraint that the field is real appears here in the fact that this coefficient is just a complex conjugated for this one, where this is just a complex number, an arbitrary complex number. This is the most generic solution to the Klein-Gordon equation. You give me initial conditions, so the field at a given time and the momenta, and that will fix my coefficients and will fix my particular solution. So that was the classical theory. We also discussed energy, energy momentum, and momentum. And now what we want to move is to the quantum theory. So to the quantum theory, to quantize the theory is quite straightforward because it follows the same steps than the quantization of the harmonic oscillator. So we have classical solutions. So what we have to do is to promote the field to an operator on a Hilbert space that we will define in a second. And to do that, what we do is to promote these coefficients to operators. So this will be a operator, element of the basis, omega t minus kx, 2 omega, plus a dagger operator. Now, because an operator, the complex conjugation goes to a emission, or to a dagger. 2 omega. And for the conjugate momentum, exactly the same. The conjugate momentum is just, remember, the time derivative for a free Klein-Gordon field. So we just have to take time derivative of here, which will bring minus I omega here and I omega there. So these are our operators, and we say always that A is the positive frequency part of the field and A dagger is the negative frequency part of the field. And now we have to define in which Hilbert space these operators are acting or are living. So from these equations, it is easy to isolate the A and A dagger coefficients operators in terms of the field and the momenta. And this is something that I leave for you as homework. Check.
I have a quick question. In the earlier classical theory, we said that the phi x solution was equal a to the e plus a star to the e. But here, we just wrote is equal to the Fourier transform of some phi k, and then that phi k now equals a to the a plus a star to the e.
Say it again. In the classical theory we did.
Yes, because phi k is the
We
function that satisfies the harmonic oscillator equation. Phi x
Okay. Oh, phi x was not the one that satisfied.
No,
the
when we
harmonic
go in the Fourier transform space, that's when we get that phi k satisfies the harmonic oscillator equation.
Okay, I was confused because I thought normal phi x satisfied that harmonic
So phi k
oscillator.
would be written as the.
So you mean, I see.
The thing in the parentheses, I thought that was just phi x, not the Fourier transform.
No, I mean, this is not either the Fourier transform, but this can be written as, this could be written if you want to have this phi k.
Yeah.
Remember that the phi k we had the exponential of I kx outside.
Oh.
But you can do that. If you change variables in the second term from k to minus k, you can check. And it's a simple exercise that this equation can be written as 2 by q. Then ak. I forgot the k's in the a's. I'm sorry. Same here. Of course, a depends on k. One a for each. E to the minus I omega t plus a dagger of minus k e to the I omega t, everything multiplied by I omega, I kx.
So that parenthesis term is the phi k. and
This
that's
is the
what
phi k
satisfies-
that it was defined before.
Oh, okay.
Yes, just more common written in this way, but it's exactly the same. So you can check that this is equal to this by changing variables here and taking the exponential outside. Sorry, I forgot the case there. That is important. So what I was saying is that from these equations, you can isolate the operators A and A dagger in terms of the field operator and the conjugate momentum. It's just a simple exercise to write it in the following way. It's you need an x integral, the field, partial t with this double arrow that we will define in a second, e to the I omega t minus kx divided by 2 omega. And a dagger is just the mission conjugated. So you just have to take the mission conjugated. The field is a mission, so we have to do nothing with it. Partial t with 2 arrows.
What is that 2 arrow?
I will define it immediately. T minus kx divided by 2 omega, where of course, sorry, with no arrow, remember that this is the for an event, so it has t component and an x arrow component. So first of all, these two integrals doesn't depend on t, because these coefficients are independent of t. So you can evaluate them at the time that you want. The result is exactly the same. And also the arrow, you have two functions f and g. This is by definition the derivative acting on the second one minus the derivative acting on the first one. So 2.3. The interval, these expressions are time independent, so it doesn't matter which time you use to evaluate them, and it's your homework to check that that this is the way of isolate this. So this is nice because now we have a and a DAG operator in terms of phi and the conjugate momenta, because whenever the time derivative acts on phi, we will have the conjugate momenta. So we can use from these equations, I think I am giving them a name, 4. These equations 4. And the canonical commutation relations. So the fact that phi of tx, phi operators tx prime is equal to I delta Dirac x minus x prime. From these two pieces of information, we can obtain the commutation relations for creation and annihilation operators, as we did for the harmonic oscillator. These are 0. All creation commutes with all creations. Now they are non-trivial because we have different k's, so we have to check that k and k prime, they still commute, and they do. You can check that. In fact, this is something that I want you to check. And also the non-trivial one is this last one. And
will my E depend on T of none?
say it again.
Will my E dagger, I mean the E hat, E operator, will that depend on time or not?
They don't depend on time. They are time independent. Otherwise, this guy at the classical level is not a solution of the equation of motion, because this is a solution, this is a solution. So a linear combination with time independent coefficients is a generic solution. So A and A dagger are time independent coefficients in the classical theory and operators in the quantum theory. This is what I emphasize here. I didn't write it, but I said it in words, that these intervals, you can check that they are independent on which time you plug it. You can check that. You do these intervals explicitly, and the time dependence disappears. And this one, because of the conventions that I used for the basis of the modes, they have these factors here and a Dirac delta in momentum space. So they are proportional to h bar as in the harmonic oscillator, and now because I am using this convention, you have this 2 pi cube here, and of course this delta Dirac because k and k prime are continuous. So they are 0 when k is different from k prime. Again, these 2 pi's are just conventions. So in some books, the people introduce the 2 pi's in the modes, so in the basis of solutions, and then you don't have this 2 pi here. It's just a convention. I think in Minkowski spacetime is common to have that 2 pi cube there, but you can just remove it. And as for the harmonic oscillator, this commutation relations is what provides A and A dagger, the name of annihilation and creation operators. For the same reason as for the harmonic oscillator. So I'm not going to repeat the exercise. For for each k. So we have an infinite amount of couples of creation and annihilation operators, and the operator dnk h minus 1 a dagger k ak operator. Sorry. This operator, I call it dn operator. It is h minus 1 d3k, the 2 by factor a dagger a for the same k is called the differential number operator. Why it's called number operator? Because its expectation value is equal to the number of quanta with wave number k in the range k plus d3k. So the difference with the standard harmonic oscillator, with a single harmonic oscillator, is that here, k is a continuous variable, so we need to define this in this differential form. So because k is a continuous variable. But that beyond this difference, which is is normal because k is a continuous variable, this is exactly the analog of the number operator for the single harmonic oscillator. So if you want to know the total number of quanta in any k, what you do is you integrate this over k, and that gives you how many quanta some quantum state is going to have. The other thing is completely the same, equivalent to the harmonic oscillator. So now, as you may expect, one defines the Fock vacuum, so the vacuum state, as the state that is annihilated by all the annihilation operators for all k. Take all the annihilation operators, the state which is annihilated, that is called the vacuum state. The one particle Hilbert space is the space spanned by states with just a single quanta over the vacuum. So take all states of this kind for all possible values of k. You have infinitely many. You take all possible linear combinations, and this is what we call the one particle Hilbert space. And of course, it's infinite dimensional. For the harmonic oscillator was one dimensional. Now we have infinitely many harmonic oscillators. It's infinite dimensional. And the Fock space, or more appropriately, a dense subspace of the Fock space, and this comment is just parenthetical, so we will go over more details on that in a later chapter. The Fock space, which is our Hilbert space, is spanned by states of this kind. So you take creation operator for the mode k1 to some power n1 dot creation operator for the mode km to some power nm, act on the vacuum, do this for every k and for every integer number a1 nm, take all possible linear combinations, and that is the Hilbert space. Completely analog to the Fock space. This is our Hilbert space. You can check that, or by definition, if you want the norm of so you can check that the norm of states. So as a check, you can check that the norms of this kind of states, of this type of states, if I give the computations correctly, is something like Q by Q n1 h bar n1 delta of 0 to the power n1 dot dot dot, and the same for nn. nn h nn delta of 0 to the power n. And the last comment, since creation operators for one k and creation operators for a different k always commute, that means that these kind of states are symmetric under the change of particles. You can change the order of particles and nothing happens. That is equivalent to change the order of creation operators. So these states are symmetric, therefore this theory describes bosons. So this is a bosonic constant. For fermions, what we have is anti-commutation relations. So the order of 2 adagas gives you a minus sign. So that means that the states are antisymmetric under the change of particles. But we are with bosons here.
So starting from kind of harmonic oscillator description and elevating everything in quantum mechanics, we were kind of led to a system of bosons only?
Depending on the field that you are describing. If you start with a fermionic field,
So
then
we haven't even specified a field yet, have we?
no,
Or-
we have a scalar field.
That one.
Which classically, even you can check that what we call a spin, which is part of the Poincare group, is 0.
Oh, okay.
So I didn't go over that because but all these angular momentum generators, you can also study what is the spin, and for this case is 0. So at the classical level, we know it has integer spin, and therefore we know that the quantum theory is consistent if we use computation operations.
Oh, okay.
For fermions, one is driven to anti-computation operations.
But to get fermions, we start with a different field.
Exactly, with
Okay.
different action and a different.
But then we run through these steps.
Right, and then you realize that you need anti-commutation relations to have
Oh, okay.
consistency in the theory. And therefore, the states that you describe are antisymmetric if you change the order of the particles. And they are perfect. In our case, we have. So this is the quantum theory. I don't need to give you more details because this is the same as the harmonic oscillator, just that we have infinitely many harmonic oscillators, one for each k, and they are decoupled from each other.
So is it like, I mean, real antiscalar is necessary for boson, or like we need to have free association?
No, so you can have also bosons with a complex scalar field,
Yeah.
so that is also possible. And even if you have interactions, you still have bosons. So even if I add here a term which is phi cubed, so the equation is non-linear, these are self-interactions, you still have bosons. So for having fermions, you need a different kind of field, different Lagrangian made of spinors. And again, we have constructed the Hilbert space, the Fock space in this case, in this operational form. And then these operators, this is a representation of the quantum operator on that Hilbert space. Because you know how to operate. You give me any state, and because I know how this guy acts, I know how this operator acts. So this is a representation. It's Hermitian, because this operator is Hermitian. You can check that this and this guy satisfy computation relations, so this is a quantum theory. And with this operational definition of the Fock space, you have all the information to do any computation that you want. Can give you any state and any operator made of products and sums of these two guys, and you can compute the expectation values, you can compute time evolution, you can compute whatever you want. and we will give more details about the focus space later on.
Scalar field is specifically spin zero, right?
Yes,
Okay,
by definition of the scalar field.
yeah.
You can have vector fields like the vector potential describing the electromagnetic field, or whatever, they have higher spin. Okay, now I want to make some comments about.
Is that check a homework check or just a playful check?
Yes.
That's a decision. Stop.
It's not in red, so it's not
Oh,
how. I am tempted to put it in red.
There
So
was
let
a
me
later check that wasn't in red too.
I think that was a playful check. as well.
let me make some comments about this construction. So the first comment is that, this construction is unsatisfactory from a mathematical viewpoint. For several reasons. One of them is that I just wrote for you in that check what is the norm of the states in our Hilbert space. In this check, this is the norm. And the norm is full of deltas of 0. And that is indefinite. So the norm of our states are proportional to the delta Dirac of 0 to several powers, and this is indefinite. You didn't complain, but you should, because I have a Hilbert space with indefinite norm. What do I mean by that? So do you know why that happens? Do you guess what is the source in my construction of that?
Infinite harmonic oscillators.
No.
I mean, if we have infinitesimal vectors, then
It has to do with that.
it has
So
to
we
be
have,
that.
if you have infinite harmonic oscillators, each one has some ground state energy.
I think that's
that-
a different problem.
that is a different
And
problem.
That
also
is a
we have
different-
infinite number of points in space-time.
Ready with that. So these 2 points is a different problem. We will have it, but this one has more to do with that. So that delta comes from this delta. So this is the origin of that delta of 0, because you use commutation relations to, you have the bra, you have the ket, you use commutation relations to compute it, and every time you compute 2 of them, a delta appears. At the end, all k and k prime have to be the same. You have a 0 there. So this is responsible for this. Why this appears here? Because k and k prime are continuous. Wow. This is the problem. So
Is this where the extended Hilbert space, or whatever Daniel Cutter talked about, came into play?
no, yet.
Not yet, okay.
This is a consequence of using plane waves. This exponential minus I omega t minus kx with this normalization and the complex conjugated as our basis, as the basis of the complex, of the space of complex solutions. So why? Because they are labeled by a continuous. They are labeled by a continuous label. Redundant sentence. So as a consequence, we have that this kind of commutation relations are forced to be proportional to a delta function, and that delta function is spoiling our normalizations. Just just to tell you what is the proper way of doing it, a more convenient strategy is to use what we call wave packets as basis. you know, even in quantum mechanics, states with definite wave number or momenta, they are not normalizable. They are normalizable to the delta Dirac. So physical states, they are peaked in some value of k, but with some width. So you have some contributions from other guys. It is not exactly definite momenta. So one can use those, for instance, a way of constructing those. Let me label them now by a discrete index. They would be made of just superposition of or linear combinations of our bases with some function here, f, which is a function of k, and depends on some particular k, ki, and this is a function which is normally highly peaked on a particular value, a constant value of ki. So you know, this is a combination of these guys with a function which is highly peaked on ki. So this is like this guy for ki, but smeared with some other contributions.
I have a question.
Please.
So this structure of the Hilbert space seems to be very similar to what we do for electron or like a single particle on the real line, where we introduce the position and momentum basis, which also has this delta normalization.
Right.
And of course, we know that the square integrable functions is only a subspace of that. So there, the standard mathematical picture is to use rigged Hilbert spaces, where you have this Gelfand triple, where you take Schwarz functions and their dual, which are these distributions containing position and momentum eigenstates, and then having the Hilbert space as being larger than the Schwarz functions, but smaller than these distributions. Can you do exactly the same here? And is it just a one particle Hilbert space, or like how does that fit in for the full Fock space?
So you can also do it. So you can construct the one particle Hilbert space from those functions that you were mentioning, and then from the one particle Hilbert space you construct the Hilbert space, the full Fock space, and that is a mathematical rigorous way of solving this problem. But and I will probably describe that in more detail in chapter 10. But this way, which is is a shortcut, is also a valid way of doing it, just considering wave packets, and because it's simpler and it's more popular in standard textbooks, I want to start with this one. But you are completely right. So one way of doing it is using these Schwarz functions, and for the one particle Hilbert space and for the Fock space built from it. So thank you for the comment.
Okay, thanks.
And so you can just smear this plane wave with some highly big function and have a basis with a discrete index of wave packets, and we will see an example of that maybe in black holes. When we compute Hawking radiation, we can see here I am just writing F. I will give you concrete examples in practical situations, like in black hole radiance, if we have time. I just wanted to tell you that even though when you see those infinities there is a better way of doing it, and when you do that, then for instance, the creation and annihilation operators will carry a discrete index, and then you will have a Kronecker delta, which is not infinite. When I is equal to j, it's just 1, and everything is well defined. So, therefore, you can wonder why every book uses these plane waves and those non-normalizable states. The reason is simple, because they are much easier to manipulate. If you try to do computations with wave packets, these intervals, these functions are always in the middle, and it is a nightmare. So what people do is use plane waves with these non-normalizable states, keeping in mind what the problems are, and because they are easy to manipulate, and at the end of the computation, if you want, you move to real wave packets. So you just keep in mind that those infinities are an artifact of your basis, but if you are happy doing that in the intermediate steps, then everything goes fine. So this is the first comment I want to make. The second comment I want to make is the following: is regarding Lorentz invariance here in Minkowski spacetime, in particular about my conventions. And the statement I want to make is just, in Minkowski spacetime, Lorentz invariance is quite important. So if you read a book of quantum field theory in Minkowski spacetime, the conventions that they use for the 2 pi's, etc., is different from mine. And the reason is that they want to have everything Lorentz invariant. So in particular, you will find that for Fourier expansions, I use d3k over 2 pi. If you change that to d3k over 2 pi cube divided by 2 omega, this guy is Lorentz invariance in the space of the momentum space. Lorentz invariance. I use this normalization for the modes divided by 2 omega. So in quantum field theory Minkowski spacetime books, they don't write the denominator. Because if you do that, then as a consequence of this, the commutation relations for A and A dagger acquire a factor, which is normal. I erase it, but so they are H bar, normally they put equal to 1, 2 omega delta 3 k minus k prime, and you can show that this is a Lorentz invariant combination. Of course, the physics doesn't depend on the conventions, but if you plan to work all the time in Minkowski spacetime, probably it's a good idea to use these different conventions, because then everything is Lorentz invariant. But in my case, because I plan to abandon Minkowski spacetime in a lecture, so I will keep working with this, because this is what people use also in cosmology, etc. Just to tell you that, they are not Lorentz invariant, but there is no problem. One can do it if you want changing the convention. The last comment, which is important, is similar to what we did for the harmonic oscillator, and is the following: is that the construction of the quantum theory can be written in a more compact way. And we are going to do it. Remember what we did for the singular harmonic oscillator? So what we did is to go back to the space of solutions and introduce a product on it. It wasn't definite positive in the space of solutions, but it was positive definite in the positive frequency subspace. And with that inner product in the positive frequency subspace, we were able to write all the expressions in a very compact way. So I'm going to do the same here. So first step, write a product on the space of solutions. So first define a product in the space, the vector space of complex solutions to the equation of motion. So, and of course I want a product, remember, it's a product between solutions, but in order to be well defined, the result of the product has to be a number, not a function of time. So it has to be a conserved product. Because if it's a function of time, then it's ill-defined. I don't know when to evaluate it. I want it just to be a number. So I need some conserved product. In the singular harmonic oscillator, the Brownian gave us the idea, because we know that the Brownian of the differential equation is conserved, so I was basing my product on that. Here, in order to find a nice product, what I'm going to use is a very natural element associated with the differential equation, which is the only conserved current that the differential equation has. So it is obtained, and you will see why I want a conserved current, because it's simple. A conserved current always has a conserved charge associated with it. So what you have to do is take the current take the zero component, integrate it in a spatial hypersurface, and that is a conserved quantity. So this is what I'm going to do. So it is obtained from what we call the Klein-Gordon conserved current. There are different ways of doing it. One also can use the symplectic structure of the phase space, and maybe I will do that later on. But a natural and simple way is to realize that in the Klein-Gordon theory, the classical Klein-Gordon theory, there is a current. So now I am back in the classical theory. I am working in the space of classical solutions. So a current J, which will depend on two solutions. So, and given those two solutions, the current is just the first solution, complex conjugated, partial mu, the second solution, minus the first, minus the second solution, the first solution with derivative complex conjugated. This is the definition of the Klein-Gordon current for two solutions. So the key property is that it's a conserved current. So the statement here is that this current is conserved. That means that if you take derivative of the Klein-Gordon current and you contract the index, you get exactly zero. Checking that is quite simple. Of course, it's zero if phi 1 and phi 2 are really solutions of the Klein-Gordon equation.
Is this product only for these wave packets?
No, this is for any element in the space of
so
solutions.
var phi, phi.
This is a different point.
Okay.
So forget about wave packets, come back to the space of solutions. Wave packets are inside the space of solutions because all linear combinations of plane waves are there. But this is just a current defined in the whole space. Take two elements of the space of solutions, whatever element, and this is the definition. And the statement is that that current is conserved for any two solutions. The proof of that is simple. Just take this and take derivative and see if we get zero or not. So you can take this. We have two terms. So with the derivative, we are going to have 4. The first one is partial mu of phi 1 conjugated partial mu of phi 2 plus partial 1 partial mu this minus partial mu phi partial mu upstairs phi 2 partial 1 conjugated minus partial phi 2 partial mu phi 1 conjugated. This is what you get just applying the derivative there. You can see that terms with two derivatives, this term and this term, are exactly the same, except for this, because the two derivatives are contracted, so you can move the indices up, upstairs and downstairs if you want. So they are exactly the same, except for the sign, they are 0. And for these other two terms, you have to realize that this operator is just the box operator. So we can now use the fact that these two guys, are solutions of the equation of motion. Everything fell down, or only one person left?
I'm not sure.
Brajesh, are you there?
Yes.
So if two guys are solutions of the equation of motion, so they satisfy the equation of motion, box phi 2, remember the equation of motion is box phi minus mu square phi equals 0. So this is going to be phi 1, and this is going to be just mu square phi 2 using the equation of motion minus phi 2 mu square phi 1 conjugated.
I don't know how.
So this is equal to this, and this gives me 0. So therefore, that current is covariantly conserved. Is everything fine, Javi?
I think if someone has to call, if someone went offline, they call and
Okay. So why it is nice to have a conserved current? Because you know that if you give me a conserved current, then we can immediately construct a conserved quantity. So then we can construct, we know that the integral, so if you give me some inertial observer, you take J, Klein Gordon, you take the 0 component, and this quantity is time independent. As a direct consequence of that, and of course, appropriate follow-up boundary conditions.
We wanted our norm to be constant. That's why we want a...
Exactly. We want to define a product which doesn't depend on which time we evaluate it. So a product in the Hilbert space, in the space of solutions, which between two solutions, but doesn't matter which time, because if it depends on time, then it's not really a product. It's something else. So as a consequence of that, we have that. So we can use that as our product. You know, historically, this current play an important role in the construction of quantum field theory, because as we were discussing the other day, you know, Schrödinger equation was the quantum theory that people had, but it's not relativistic, so people wanted to make it relativistic. That was the origin of the Klein-Gordon equation as an equation for a quantum mechanical system which is relativistic, where phi should be interpreted as the wave function. But in order to have a well-defined quantum theory, you need that probabilities are conserved. You are able to define probabilities and they don't change with time. For the Schrödinger equation, we have a probability current, which is conserved with time. So the question is, if there is a probability current, which is conserved in time for the Klein-Gordon equation. And somebody said, yes, I have one. This is a probability current, which is conserved with time. The only problem, and this would be the probability. This integral would be the total probability at a given time, and is conserved with time. The problem is that this is not positive definite for the same phi. So if you take phi, the same phi, you compute this for many phi's, it's negative. So it cannot be interpreted as a probability. So this was one of the main reasons why the interpretation of the Klein-Gordon theory as a quantum mechanical theory failed, and induced people to consider it as a field theory, as a field that will create and annihilate quanta on a Hilbert space. So this current played an important role there, and we can use it because it's a conserved current. We don't care if it is, if it is non-positive definite here. That already happened for the Wronskian in the harmonic oscillator. So therefore, we define a product in S as the following. So by definition, this is called the Klein-Gordon product, and it's just the integral at some time t, doesn't matter which time you use, of the 0 component of the Klein-Gordon current. So phi 1 partial mu, phi 1 conjugated partial mu phi 2, minus phi 2 partial mu phi, time derivative, because we have to take the 0 component of the current in order to have a conserved quantity. This is the definition of the product that one uses in the space. So this is what people call the Klein-Gordon product. And it plays a key role in the construction of the quantum theory, and it will play a key role in quantum field theory in core spacetime. So again, it's just this quantity, where the 0 here is implicit in the time coordinate that I am choosing. Because 0 was new, so. So now we have a product on the space of solutions, and you know, it is conserved, so it is well defined as a product. It is conserved. Doesn't matter which time we use to evaluate this integral, and also it satisfies all properties, and you can check that, properties of an Hermitian inner product in the space of solutions, except the original problem. It is not positive definite. So it's not a real product on the space of solutions.
I'm sorry, what is that T in the integral mean?
This is some T or T naught or some time that you choose to
at one
evaluate it.
specific time.
Right.
We integrate
Right,
it.
because these guys are functions of space and time, so you need to fix the time. You first take the derivative, you fix the time, and do the integral.
So this product is not invariant under time.
It is invariant.
It
This
is.
is it is conserved. Doesn't depend on T naught.
So it doesn't matter which T naught we
Exactly.
choose, we'll
Doesn't
see.
matter with T.
Okay.
And I mean, this was in fact always motivation. That I was looking for a conserved current because I knew that if I find a conserved current, the integral of the zero component is time independent, and this is precisely what it is. It's the zero component of that conserved current iterated.
Is this a check problem?
No, I already did it for you. I already did the problem for you.
No, the one that you said, the upper right corner there.
It doesn't say check.
There's no red yet, so I'm gonna.
You wanna
choose
check?
The B.
If you want it.
No.
So it's quite simple to see that, you know, it's linear in the second entry, it's antilinear in the first one, it is Hermitian. Sorry, I forgot something. There is an I here. There is an I here. Thank you. That I is important to have it Hermitian. So that you change the order, it gets a complex conjugation. Thank you. I forget that. It is not positive definite in the space where it is defined. But we have the following properties, and I want you to check this. But it satisfies the following. It's exactly the same as for the harmonic oscillator. And this is a check for you. First, recall that we have written the space of solutions as the sum of the positive frequency subspace and the negative frequency subspace. So we have this natural decomposition in positive frequency, where a basis, where states labeled by k phi k are functions, solutions of this type. Through the square of 2 omega. If you take these guys for all k, this is a basis of S plus. And of course, if you take the conjugates, this is a basis for all k, this is a basis of S minus. So just remember that, we said that explicitly before. So with that in hand, one can check that this product satisfies the following. First of all, the product is positive, definite in S plus. So it's not positive definite in SC in total, but yes, it is in the positive frequency subspace. That is a nice property. Second property is negative definite in the space of negative solution, negative frequency solutions. So in the complex conjugate. Third property, the product or the positive frequency subspace and the negative frequency in subspace are orthogonal. So you can check that if you take the product of any element phi 1 with some element phi 2 conjugated, where phi 1 belongs to S plus and phi 2 conjugated belongs to S minus, this is always 0 for all for n. So they are really orthogonal subspaces. And the fourth, let me do it over there. The fourth property.
What is positive definitely?
It's always positive.
Always positive.
But this product can be negative, which
Right,
is annoying.
That means that if you take the norm of one element, so if you take the product of phi with phi, this is always larger than 0, and 0 if and only if the function is 0.
That's what we want.
Right.
Zero
This is what an inner product must satisfy.
Okay.
Is that phi sub k adjoint is the basis of S negative, or is that just a star? I'm sorry.
This is just a complex conjugation.
Okay, cool.
Remember, we are in the space of classical solutions. No
Okay.
operators here. They are just functions. You know, I wrote phi star just because I didn't write e to the plus I omega d minus kx over through the square root.
Okay.
To go faster. And the last property is that the basis that we are using, the basis made of these guys and the complex conjugation of these guys for all k, this is a complete basis of the space of solution, is orthogonal, is an orthonormal basis in the following sense. And I put quotations for the following reason. If you take the product of any two element of the basis, you will get 2 pi cube delta of x minus x prime. This 2 pi cube is the reason why I write quotations, because they don't have norm 1, but they have norm 2 pi delta. And the negative frequency modes, they have the same norm with a minus sign, as it must be, because the product is negative definite in the space of negative frequency modes. And as I just said, if you take a positive frequency mode and a negative one, this is 0 forever, for any. Completely parallel to what I did for the singular harmonic oscillator. Okay, now I define this product. So I have that product with those properties. Now I want to use it. I want to use it to write the quantum theory in a more compact way. Again, you may think that this is unnecessary, complicated for a field in equality spacetime. You are right, but that will be extremely useful when we don't have, we are in a generic spacetime. So that will be our guiding principle. This product will play a key role.
So this very same product can be used in more, let's just say, annoying geometries.
Right.
Minkowski
Annoying
space.
or nice.
Yeah.
With the appropriate generalization. The derivative will be covariant derivative.
Oh, okay.
Interesting.
That's right.
Okay. So with this, I did it for the harmonic oscillator, so it's easier for you because here we have many Ks and that, but it's exactly the same. With this, the quantum theory can be constructed as follows. So remember, what we have in our hands is the space of complex solutions as in this decomposition and a basis. Sorry, a basis and the inner product. A basis, which is the basis of plane waves that we are using, this guy and this guy complex conjugated for every k, and the inner product. The product. So with this in our hand, the quantum theory writes in the following way. The Heisenberg representation of the phi operator is going to be just a linear combination of the element of our basis. So some coefficient, our basis. I don't write it, but the basis depends on t and x. They are plane waves. Plus the dagger. The conjugate momentum is the same. Just it's the time derivative of this guy. Then from here, the annihilation operator so this is the useful part, that you know. Now you can see that your field operator is just a linear combination of your bases. Of course, satisfy the wave equation because your bases satisfy the wave equation. So you can think about A and A dagger as the coefficients of the linear combination. But the basis is orthonormal. So we have a nice way of extracting the coefficient. How do you extract the coefficient? Multiplying your vector by the element of the basis that you are interested in. This is the coefficient. If what you want is this other coefficient, you have to multiply by this element of the basis. And put a minus sign because this guy, sorry, and I have also to multiply by the, maybe I am forgetting a 2 pi cube somewhere. I think I am forgetting a 2 pi cube. I didn't write here. Because the basis doesn't have norm 1, they have norm 2 pi cube, so I have to divide by the norm. And the same for this coefficient, the only thing is that this guy has norm minus 1 over 2 pi cube. And you can see that these expressions are much compact than all the intervals that we were writing before. And one can also check that the commutation relations for the creation and annihilation operators are given by h bar, the product of the basis that we are using, and I may be forgetting a 2 pi cube, so with a minus maybe in the denominator. I will double check and let you know. The product of two creation operators is just the same, but you have to multiply phi by phi star k prime, and we knew that this is 0. We wrote it here. And for the daggers, you have something similar. You have also minus h bar phi k star phi k. So they are negative frequency times positive frequency, they are orthogonal. And this, remember that this was 2 pi cube delta 3 k minus k prime, which is what we wanted. Maybe I will not forget it any. The norm of this state was exactly that. So it's a very nice way of codifying the commutation relations. And the important thing is that this is true for any basis. So we did it before for plane waves, but this construction can be done for any basis that we want. So this is the important thing of this that I will really emphasize when we have time-dependent situations. At this point, it's just a more compact way or more geometric way of writing what we had before.
So for differential equations, for which plane waves are not a solution.
Right.
Then
Right.
you don't have plane waves.
Right. In
Then,
core.
does that imply all the infinities that you pointed out before?
I mean,
Because
depending,
we have different waves.
you have to choose a basis there, and if the basis is
It's not plane waves. So
they are not plane wave or they are something not similar, then that will not happen. But we will see that. And and the focus space is constructed in the standard way. So the vacuum is the state annihilated by all A's, and then you construct one particle state, two particle state, three particles, n particles. You take linear combinations, and I want you to check that this is true. Questions about this?
I think I'm only slightly tripping up on the fact that we have a phi that looks normal and then a squigglier phi, and are not catching the difference. But phi hat is just the integral of that, and these squigglier phi's are just elements of the solution space.
Right.
Okay.
So phi is the field operator, and
Which
we
one's
have
the field operator?
sorry.
Which one is the field
The
operator?
field operator is the one it has hat.
The hat one is the field
Right.
operator.
Phi hat is the field operator, and we have written it as a linear combination. This is the sum
Of
of
the solution.
a basis of solutions.
Multiplied by a hat.
Right, by coefficients that, if this is an operator, the right hand side must be an operator,
Yeah,
so this
okay.
guy needs to be an operator.
Okay.
But these are just a basis of the space a basis of the classical space of solutions. But once we have a basis of the classical space of solution and the inner product, the quantum theory goes through quite straightforward. Okay, so in the last 15 minutes I want to start the discussion in the third point of the chapter, which is energy and momentum normal ordering. And momentum normal order renormalization. I do this here with some detail because I will save a lot of time in next chapter. Once I have this presented for you, it will be quite straightforward to generalize. So please understand this construction, because this will be the key mathematics that they will use in core spacetime. So if you want to understand the rest of the course, Unruh effect, Hawking effect, please understand this mathematical construction, because it's the key part. So it is worth to spend 2 hours just doing the computation by yourself and making sure that you understand everything. Okay, so now let's discuss about energy and momentum in quantum field theory in cosmic spacetime. So we described the classical Hamiltonian in last lecture. So now all we have to do is put a hat in the Hamiltonian, and the Hamiltonian was written as a combination of products of phi and pi. So we put hats, and we have a quantum operator. So the classical Hamiltonian when promoted to an operator is classical Hamiltonian, doesn't depend on time because it's a conserved quantity in cosmic spacetime. It is given by an integral. Remember that we needed a specific inertial observer to define this gentleman. 1/2 of momentum operator squared plus the divergence of the position operator squared plus mu squared phi squared operator. This is the Hamiltonian. Of course, both pi and phi depend on x, on the space-time point, and do the integral, and the statement that the result doesn't depend on time, because the Hamiltonian is a conserved quantity. Straightforward. Now, if you want to have the Hamiltonian in a form ready to be acting on states, what we have to do is to change or to write pi and phi in terms of the creation and annihilation operators. So phi is the what we have written before, and pi, the time derivative, which is the time derivative here will appear, and these are plane waves, so minus I omega will go down. So if you do that, and you manipulate it, and here I have another present for you. If you have done quantum field theory in cosine design, you have done this computation. So just copy what you have in your notes. And so you can check that this is equal to the following interval. Omega over 2 of A dagger of K, A of K, plus the other way around, A dagger of K. So this is your energy operator, and you want to call this equation 5. One can also, trivially write this. So we have A dagger A dagger, but we can use commutation relations and convert this term to A dagger A plus the commutator. So just let me do it because I will use it. 2 pi. I am losing I think I don't have the 2 pi cube in my notes. I think it's because it goes away.
Is that also a homework check?
This one, a present.
Okay. It is right.
I missed that one, but you said so.
Just use the commutation relations. We have 2 of these factors that cancel the 2, and we will have 1/2 of the commutator, which is, I am also taking an h bar away, so we have energy here. So a dagger commutator with a dagger commutator. So this is our energy operator, a straightforward application. So let me call this second form 6. They are exactly the same. And remember what we did for the harmonic oscillator? For the harmonic oscillator, what we have is that the Hamiltonian operator was just h bar omega, the number operator. So now, and some 1/2 of h bar omega. So, and the 0 point energy. Now we have the same. The only thing is that we have to that for each single k. We have infinitely many oscillators, so we have the energy of each oscillator times the number of quanta plus the vacuum energy. So this is obviously the vacuum energy.
But
It's the vacuum energy because this term will kill the vacuum. So if you apply the Hamiltonian to the vacuum, this is 0, so this is what you get. So
not only are there an infinite amount of those, it's that commutator equals delta 3 of 0.
that is floating.
So it's also an infinite amount of infinities. Okay.
That's a nice way of doing it. So another way of writing this, I want to describe now precisely what you are saying. So another way of writing this, remember that this 3k, maybe I think I am forgetting a 2 pi factor. Let me 2 pi cube.
They all should have 2 pi cubes, right?
Sorry.
Even the top one should have 2 pi cubes.
If it's here, it's here, but this is where I don't know because I changed my notation in the middle. So let's use units in which 2 pi is equal to 1.
Okay.
Perfect. Cool. And 2 and minus is equal to 1. So this is just the differential number operator h omega plus the integral in k of the 0 energy of each single k. This is the form of this guy. This is the number operator, the differential number operator, times the 0 energy for each single k. And what we want now is to discuss this. So in some respect, it's similar to the harmonic oscillator, but there are important differences. So problem, this guy, this Hamiltonian, is doubly divergent. First, as you just pointed out, this second term has so we have this interval. This is the second part there. Omega 1/2 of a Daga commutator with a commutator with a Daga. But remember that this is delta of 0. So this is 1/2 of h bar 2 pi cube delta 3 of 0. And this delta 3 of 0 diverges. This is one of the infinities that we like. Can somebody guess what is the physical meaning of that infinity?
The ground state energies of every single point in space, every single particle.
That is the other one.
Oh, right.
We have an infinite number of harmonic oscillators that have a non-zero vacuum, or
This is-
non-zero ground state.
This is the other divergence. So there are two divergences here. One, because this is divergent.
Yeah.
But even if this is one, if you sum something finite for every k, that will blow up. So this sum is what you are pointing out.
Yes.
But this divergence is something else.
But that's
That's the
due to
continuous,
what we talked about earlier.
whatever.
Right?
The continuous index,
Space-time.
or continuous, yeah.
Yes.
Isn't it?
Well,
So let me write this in a different way. Remember that this is the total energy. I think that will appear even if you use wave packets. So that is the
What is the argument of 0? Is that position or K?
that is
no,
K.
no,
That is K. This is the because this
The zero
comes from the
vector.
commutator.
Okay, so that's a spike at the origin, and
So it's
instead
just
of K
infinity.
equal to 0. But omega is an argument of K.
And therefore
So it,
delta 0.
it has an e
it's
to
the
the
k
I.
minus k prime, but k prime equals k, so it's just
Okay,
0.
you go in the right direction. So
Yeah.
let me write the representation of the delta function. This is 3x e to the I k 0. So this is the delta of 0, isn't it? So this is equal to 1. So what is this? 1 over 2 pi cube times what? This is the volume of a space-time, of a space. And the volume of a space is infinite. So this divergence is because, because the energy of the total space, if the space is infinite, is divergent. So where,
So is the ground state energy of each one also infinite?
yes.
That's odd. Okay. Cool.
So let me say it properly. Is the volume of the entire space. That's nice. So, what happens here is that, if you give me a state, a quantum state, as the vacuum, which is homogeneous, the vacuum is homogeneous, so it doesn't depend on which point you are, and you ask me for the total energy, two answers, infinite or 0. If it has some non-zero energy per unit volume, if you integrate over the whole volume, it's going to diverge. So, an artifact of having homogeneity and infinite space-time, space in this case, is what produces this particular divergence. So, in my opinion, this divergence is really expected from the physical point of view, because the space is homogeneous, and if you have 0 or infinitesimal energy per unit volume in the whole space, you are going to have infinity. So for me, it is kind of inconvenient, but not too much. And the way of dealing with this infinity is to working with densities. So if
But the space isn't infinite, right? So there is, like cosmologically, there is some positive.
but we are in Minkowski space-time, so Minkowski space-time is infinite.
Yeah, but this problem won't be there in our universe.
I think it will be because our universe seems to be spatially flat. So
But it also has especially flat at very locally when you see it locally. But overall, it is seen.
I think
Observed
overall,
from
overall,
it's
we believe it's spatially flat.
It's both locally flat and overall really flat.
So it has some space-time curvature, but if you freeze it at a given time, it's like a three-dimensional flat slice. So these kind of infinities will appear there. But of course, what we do in physics is to work with densities, work with energy per unit volume. And therefore, when you do that, you get that infinity. So the solution, if you want, the solution that physicists normally use is to work with energy. Another solution is to say, okay, let's put the universe in a box. Let's assume that the universe is not infinite, but it's like a torus, or it's still flat, but it has, topologically, it's like a torus.
Do you mean energy density or just?
With energy density. I mean density. Yeah. Density. Thank you. And I'm going to stop here, but the second problem is that what we discussed, even if you divide by the volume, so you get rid of this infinity, this integral is still divergent, because you are summing over all case some quantity which is finite. So you will get a second divergence there. And this divergence is because we have infinitely many degrees of freedom. And that is intrinsic to field theory. And this is the type of divergence which appear everywhere. So our work is going to manipulate these divergences to be able to extract physical information from our theory. So this is the first example of the biggest problem, mathematical problem in quantum field theory. One of them, which is the infinities. And the techniques that we will use to take, to extract physical information are called renormalization techniques. And we will see how to do it in this case of Nicosis this time. And do you have any question?
Can I please revisit what we just talked about a little bit, because I'm still slightly fuzzy on it. There
Okay.
are two infinities. One is for having a ground state energy at each point in space.
One is because we have an infinite space.
Number of space.
An infinite space. A non-compact spatial slices. So you take this space and you take any inertial observer, you fix t, that is a non-compact. So any integral on that is going to diverge unless it's the integral of 0.
To put that more plainly for me, we have a Dirac delta. Not only do we have a Dirac delta right there, we count it over all of space, all of K, actually.
But you don't have, I think you are mixing the two divergences. One is because we have infinitely many oscillators.
Yeah, yes, I get that. That's infinitely many oscillators.
Even if you take one oscillator and you consider the vacuum, then the vacuum for that oscillator,
Okay.
the vacuum energy diverges.
Oh yes, and the Dirac delta is due to infinitely large space.
Exactly. This is the infinite amount of volume that we have at a given time in the whole space.
So the ground state energy of that one is infinite due to the fact that we have to go through all of these.
Right. And the argument is simple. The vacuum is a homogeneous state, so it has the same, the same energy everywhere, same energy density everywhere. If that energy density is different from 0, when you integrate over the whole space, it's going to be infinite.
Okay.
But that is just, that is not really bothering me because you work with density, you make local measurements all the time. If you just want to define your local measurements in a finite volume, then you work with densities and that is fine. The other is more puzzle. The other, there is no way of dealing it is there, and we have to think how to deal with it.
So I don't quite understand why there are two, because when you make the substitution of the delta function for the integral over its volume, aren't you eliminating the delta function, which picks out the k equal to 0 component, which gets rid of the k integral and replacing it with a spatial integral? Or, I mean,
So you mean that this is an artifact of using this, having k's here and having this?
well, if that's a delta function in k, doesn't that pick out k equals 0 and?
It doesn't because it's always 0. It's not picking
No,
out.
it's not it doesn't have k inside the delta function.
No, it's
Oh,
just
I
zero.
see.
Yeah, that's the
I mean, you
problem.
can think it in many different ways.
Okay.
It's not behaving like our normal Dirac delta.
So I
Yeah.
mean, you can think it in different ways. For me, the most straightforward interpretation is that this is just the volume. But there are many ways of thinking about that. So the statement is that if you put the universe in the space in a box, so if you have finite amount of space, this integral disappears.
You can take the delta function out of the integral, right?
Right.
Yeah.
Sure, okay, that makes sense.
Right.
Yeah,
So it's not a delta of k minus 0. It's just a delta of 0. If that is
yeah.
if that is your
That's so
question.
strange, I didn't even notice why it was
Yeah.
strange. I just interpreted it as something sensible.
Any other question?
And what if like we would have taken, what is that called, this web packet?
That the same happens.
So then still we would have to.
We also have two divergences?
Yes.
Like, okay.
But they appear in a different way. But
Okay.
still,
Like finally-
the energy of any homogeneous state is 0 or infinite. That is.
Yeah, then in that case it could have been 0, right? Because it was like delta Iz, I mean.
Right,
instead of
but
delta
it will
delta-
appear in a different way.
But
Yes, so that would give me 0 or infinity.
No, that you will have an infinity at the end of the day.
Okay.
But these two infinities also stem from the fact that we're dealing with bosons specifically right now. If we had fermions, we would have infinitely many oscillators. Or
Right, you have different.
oh, okay, cool. So it's still temperature.
But I think in this case, in that case, you also find infinities because of the infinite number of degrees of freedom.
Oh, okay, yeah.
So, just,
But do the occupation of one particle per.
right,
I should say,
per
then-
k, but you have
Yeah.
many k's, so you still have the divergence.
Cool.
Any other comment? Next day we will deal with this more bothering infinity.
Boring.
Bothering,
I suppose.
annoying.
2 homeworks.